So in the previous videos, we've looked at resistors, inductors, and capacitors separately in circuits. So in this video, we're going to put them all together and look at RLC circuits and also define impedance. So and this is in chapter 33.9 of the textbook. All right, so an RLC circuit, so we're going to look at series RLC circuits where we have an AC power source, an inductor, a resistor, and a capacitor all in series. So, since these are all in series, and even though this is an AC circuit, its charge is still conserved, so it still has to be true that the current has to be the same everywhere. So the voltage, well, to get the voltage, we can actually use Kirchhoff's loop rule. So Kirchhoff's loop rule says, right, so you walk around the loop, so we have some voltage supplied by the AC power source, and voltage drop is across the inductor, the resistor, and the capacitor. So, and that has to equal 0. So we can actually use phasors to analyze this, and in general, when you have complicated AC circuits, this is what you do, use this phasor. So for the top, well, we actually put everything together. So we have the voltage across the resistor, which is the arrow here pointing to the right. So, and that has to be, remember, in phase with the current. So that has to, since the current, we drew the current as along the x-axis, the voltage across the resistor has to be in the same direction as the current, or the voltage phasor has to be in the same direction. So, and for the capacitor, so that actually the voltage lags the current by 90 degrees, so that's 90 degrees this way. And for the inductor, the voltage leads the current by 90 degrees. So we draw the voltage across the inductor as 90 degrees that way. And then the way to think about this, right, so remember the way we think about phasors is, let's say this is our current phasor, so it's going to rotate counterclockwise. So the whole thing rotates. And since these have to be 90 degrees and the voltage across the resistor is in the same direction, so they all rotate together. So at any given instant then, remember, we can find the particular voltage or currents that we want by taking the projections. So for example, and actually we can total everything up, and what we find, right, so the total voltage is the sum of all those phasors, which is like a vector sum. So it's going to be off in some direction, and there's going to be some angle phi with the current. So the maximum current then is equal to the maximum voltage divided by the square root, because, well, this is essentially just Pythagorean theorem for this little right triangle. And it's going to be the inductive reactance minus the capacitive reactance squared plus the resistance squared. And take the square root of all that. So, based on that equation, we can actually define something called impedance. So impedance, which we're going to use a capital Z for impedance, is square root x sub L minus x sub C squared plus R squared. And remember that was the denominator in that previous equation. So then we have something that looks similar to Ohm's law, where the maximum current is equal to the maximum voltage divided by the impedance. And similar to inductive reactance and capacitive reactance, it also has units of ohms. It's similar to resistance, but remember, since the inductive and capacitive reactance depends on the frequency, the impedance also depends on frequency. And if you stare at this equation, the impedance is going to be at a minimum when the inductive reactance equals the capacitive reactance. So this just gives you 0, and the impedance is just equal to the resistance. So in the conditions, so this is the conditions for resonance in a circuit. And the resonant frequency omega 0, if you do some algebra, you can show that it's 1 over the square root of inductance times capacitance. And then finally, for this RLC circuit, so remember there was this angle phi in between the current phasor and the voltage phasor. And again, if you just look at the right triangle we had in that picture, phi has to be the inverse tangent of inductive reactance minus capacitive reactance divided by the resistance.